Hi, this is the final demo we have for our senior design project, SP9. It's the FPGA accelerated Linnet application. Kind of introduce a project. Our goal was to demonstrate that a low-cost FPGA can accelerate machine learning inference on an embedded platform. And the approach we used was to capture a handwritten phone number through a USB camera, send it to our embedded platform, which was the PYNQ-Z2 board, pre-process, run a Linnet model on an FPGA and to the CPU, and then using those recognized digits, call the phone number that was written down by the user through an API. And our final takeaway from this project was that it was possible to observe a real-time digit recognition with greater than 93% confidence and up to a 14% speed up on the accelerator versus the CPU. And for this project, our design objectives, again, were to use an embedded board, being the PYNQ-Z2, the accelerator. We actually use an accelerator from the CNN IoT repository on GitHub, so we had to give credit to where that's from. It included a Linnet accelerator, a Linnet CPU architecture, so an accelerated version and a CPU-based version of a Linnet machine learning model. And for that model, we pulled the model weights from PyTorch. And again, to execute inference, we used a camera, took a photo of some digits, and sent that to the board to execute the inference.
The basic system works by taking a picture with a USB camera, which we have connected to the PYNQ board, and then pre-processing and segmenting this image. And then we send these pictures to be inferenced by Linnet on a single layer CNN. And then we display the results on our UI, and then we call the phone number.
Linnet is a CNN architecture designed for handwritten digit classification. It takes 32 by 32 grayscale images as input and outputs class probabilities for the digits 0 through 9. Our implementation of Linnet is currently using 6 layers: convolution, pooling, fully connected, and then fully connected again. First, a layer is chosen by the CPU, and then the layer is initialized via a config object sent to the hardware via DMA transfer. Then the computation of that layer is started. The output of the hardware is sent back to the CPU via DMA transfer. This result is then passed to the next layer object on the CPU in a feed-forward manner. Due to the configurable logic block constraints, only one layer is in hardware at any given time.
Hi, this is a demo for our FPGA Accelerated Linnet application senior design project. Our setup consists of a PYNQ-Z1 or Z2 board that is connected to the router directly through an Ethernet cable and is also connected directly to a webcam. And what we do is that we take this webcam and we take an image of this phone number that is then sent to our computer when we click on the capture image button. And then we go down here and we click on segment image, and as you can see, it segments all the 10 different numbers and it processes them and it centers them and it clears up all the pixels. And then we will click on predict all CPU, and then it runs all the predictions and it runs them one by one, and it ranges at about 1.2 seconds. And then we run the FPGA, and the FPGA only takes 0.16 of a second, and it results in the exact same accuracies. And so then we will go up and we will assemble the FPGA phone number, click OK, and then it would show up the phone number over here based on the numbers with the highest predictions. And then we will call the number, and it will give us a message over here that it's actually calling the number. And that's it for our senior design demo. Thank you.
On this slide, you can see our testing and evaluation, which we have. Overall, our hardware accelerator allows for up to a 14 times speed up compared to the CPU implementation of Linnet. And we have 100% testing accuracy as well as 100% confidence for the testing that we have conducted. And overall, the entire process takes under 15 seconds, with the FPGA calls taking less than 2 seconds in total.
So in terms of the data analytics, we can see from the graph that it shows the speed difference between CPU versus FPGA with that classification, where we see that the first 2 layers are convolution layers, where CPU executes way slower than that of FPGA. And the same thing, a similar thing applies for fully connected, even though it's pretty similar. And finally, for the pooling layers, we can also see that the CPU takes more time.
This graph shows the difference between the average confidence for each class when comparing the default processing along with the additional processing, specifically pre-processing that we included. As you can see in the default pre-processing, the average confidence goes quite low, in some cases as low as nearly 0.3. However, the average confidence with the additional pre-processing is consistently above 0.93, in many cases above 0.95. And so overall, the additional processing approach turned out to be 100% accurate when compared to the quite poor accuracy of the default processing technique.
So in conclusion, we found out that the FPGA accelerator delivers dramatic speed up compared to that of the CPU and even the GPU, and the pre-processing boosts Linnet accuracy, as seen from those graphs, to over 93%, and the hardware acceleration, luckily for us, didn't degrade the model performance. And in terms of future enhancements, something we could do is that we could swap in a more lighter model, such as maybe even MobileNet, and something we could also do is try deeper pipeline parallelism for further throughput gains. And finally, we can try to scale demo with the ImageNet class recognition to try to predict images in the ImageNet dataset.
This is it for our senior design demo. Thank you.